So hello nerds, this is Suman, and in this video we are going to talk about the same idea, the same relations, the same mathematical intuition but in a different perspective, right? So basically I had derived very much uh, about uncertainty principle. So you can actually visualize uncertainty principle in terms of position and wavelength, in terms of various factors, right? I have described it for massive particles as compared to photons, just like electrons, protons, and neutrons, and I had also derived it for the concept of photons, so how it apply to photon and how it apply to electrons using the kinetic energy based energy equation and the relativistic energy equation for the photons. So I'm already saying that this is not my new idea and I hadn't revolutionized anything yet. So this is the old idea. I had just put in another perspective of seeing this. So there's another kind of looking the same equation in terms of various uh, terms. So in terms of wavelength, in terms of energy, in terms of Lorentz factors, in terms of kinetic energy, in terms of momentum or whatever you say, or in terms of Compton wavelength. So uh, lastly I had uploaded three video, and the three video consist of the kinetic energy based condition. It is for photons, that is for photons, and one for relativistic condition for massive particle as compared to photon. But in this video I'm going to show you another beautiful result. So again, it is going to be the very beautiful result. If you are from the physics field, so were going to see this, so you will immediately recognize this thing. So the relation is nothing. If you can see there, whether it is seen there or not, I really don't know, but I'm expressing. So we all know that quantum mechanics is very hard, and if the people who invented it really make it hard, why we can't just make it worse? So let's make it more worse, just by putting position, energy, uncertainty. So basically, I got in relation that consists the position, energy, uncertainty is always quantized for the fact. In case of vacuum, it is always constant, or it would be greater than that quantized quantity, but it is actually approximately it is quantized. So and it is a direct consequence of energy and wavelength factor. So you can actually say that there will be higher chances of spreading a photon in space as compared to the photon when you put in a different medium like water, plexi, glass, anything you can imagine except vacuum. So there will be higher degree of uncertainty in vacuum as compared to the other medium. So and I got the relationship between it, and I will going to show you this. And if you really find any mistakes in my videos, you can actually suggest me to suggest me for the correction, and I will do my best for correction. So basically, before making the lecture, or whether I have to call it lecture or not, I had already checked out my idea. And this is not my idea. I had already checked out this mathematics various with my teachers, with chat GPT. Sometimes it is actually legit and it doesn't work properly, because even it is not human, right? So what human can thinks that they cannot. So you have to imagine something very much interestingly, so you can actually imagine the things and you can actually put it into the perspective using the mathematics, and you have to be explaining that fact based on the mathematics, so how it actually works, how it's gonna applied, and etc etc etc. And the one thing you can actually conclude from this relation, that the uh, Young's double slit experiment might be the direct consequence of position energy uncertainty. So instead of getting the two bright bands in experiment, we will get a multiple bands, and the band intensity goes on decreasing when we move relative to the central bright, right? If you have central bright here, then the another bright we obtain here, the intensity goes on decreasing and decreasing and decreasing, and rapidly it vanishes out. Whether it vanishes exponentially, linearly, quadratically, I really don't know, because I'm undergrad student and I really don't know whether it goes vanishing in which manner. So it vanishes. So Might be I it is just my guess that the uncertainty is the direct consequence of the wave nature of radiation and particle when it has associated wavelength or when it is in motion. So the main idea I want to calculate, and still I am not able to calculate it, was the actual position and momentum uncertainty. So what if we can find that relation, and if we, I think if we find that position and momentum uncertainty relation, we can actually derive the whole bunch of uncertainties simultaneously. So this is my guess, and I'm still working on it. So I had worked on this content for now, the energy position uncertainty. So let us dive into the whiteboard. So, yes, nerds. So, before deriving energy momentum uncertainty relation, I would like to convince you a very much interesting some fact. So, this energy momentum relation is actually useful for photons, not for the massive particles as compared to photons like protons, neutrons, and electrons. Because because photons is massless, and relative to other particle, photon is massless. Experimentally, it is massless, I guess. So basically, we are going to derive energy, position, energy, position, uncertainty. So let me recheck my words. Uncertainty. So we are going to derive the uncertainty relation, right? So it actually focus very much. Let me reduce the light. So the this part says that the energy, momentum, uncertainty. So so if you had already watched my previous videos, then you will understand this. And if you hadn't watched this, I'm going to derive it again from the similar equation, the same method, the same methodology, the same process. So don't be confused. So basically, you have to understand, you have to know the concept of Heisenberg uncertainty principle, right? So I'm starting from Heisenberg, uncertainty relation. So basically, Heisenberg uncertainty principle states that the position and momentum uncertainty, the product of position and momentum uncertainty, is nothing but h upon 4 pi, right? And you can write your h cut is h upon 2 pi. So you can reduce this equation into another form. Delta x into delta p is greater or equal h cut over 2. So this would be your equation number 1, right? So and secondly, you have to understand the concept of de Broglie wavelength. Okay, from de Broglie wavelength, from de Broglie wavelength equation. So from de Broglie wavelength, you can write the momentum is Planck's constant over the wavelength associated with that particular matter. So I am just going to manipulate the terms here. That is, P can be written as h over 2 pi into 2 pi over lambda. Right? H over 2 pi into 2 pi over lambda. So the momentum can be written as h cut, So it is nothing but reduced Planck's constant. Reduced Planck's constant. It is nothing but the reduced Planck's constant. So, and the 2 pi over lambda is nothing but your k. I guess it is a moment, it's an wave number. So, so you can basically write momentum in terms of wave number. So equation number 1 becomes, I'm using 2 in 1. So I'm using my 2 in 1, and what will I get here is delta x into h cut delta k is greater or equal h cut over 2. So I'm getting delta x into delta k. The product of uncertainty in position and uncertainty in wave number is greater or equal 1 over 2. Here you can clearly see that the uncertainties are always positive. So basically, you cannot measure, you do not have your uncertainty negative. So the video quality is going to be very much bad, but the concept I am providing here is very good enough. So you can actually make a meme of it saying video quality 0%, knowledge 100%. So I'm just kidding. So basically you can write your wave number, you can write this in terms of like this. So what I'm going to do, so I don't want to write it in this form, so I like to write in another form. So what would I do? So I know that the wave number, the uncertainty in wave number can be written as a rate of change of wave number with respect to wavelength. So why here we are using wavelength? Because the wave number actually depends on the wavelength of light, right? So I'm writing in this differential form and I get this. So it also makes sense to you guys. So the uncertainties can be written like this. You cannot directly put substitute the values there. You have to write in this form. So delta k is nothing but d over dk, and this k is what? This k is nothing but our 2 pi over lambda, that is 2 pi over lambda into delta lambda. So your delta k will be, if you take 2 pi outside from the derivative, you will end up getting negative lambda square by d lambda into delta lambda. So, and good approximating result. So I had already told you that the uncertainty is always positive. So I am taking the magnitude because one can say that why I didn't use the negative sign. I am just taking the magnitude because I know the uncertainties are always positive. So I am writing it as 2 pi over lambda square delta lambda. So I can reduce my equation. I can write my equation in terms of wavelength now. You can see from here. So I can actually change the uncertainty in wave number in terms of uncertainty in wavelength, right? So delta, so that the d over dk represents the derivative with respect to, sorry, it's not d over dk, d over d lambda. So one can actually already find the mistakes. So what I'm now going to do is, I'm saying this as equation number my 1 and this would be my equation number 2. I had already dropped the equation number, actual equation number 1 and equation number 2, so I can write it as equation number 1 and equation number 2. So using 2 in 1 again, using 2 in first. So when I substitute my equation number 2 in equation number 1, I will end up getting delta x into 2 pi over lambda square delta lambda greater or equal 1 over 2. So I can write as delta x into delta lambda is nothing but greater or equal to lambda square upon 4 pi. So actually if someone had actually seen this concept and he had used the negative sign, if he neglected the magnitude, so he would not have to, he must have to use the negative sign and his uncertainty will be less or equal to like this. And based on his assumptions, he can also conclude that if you're trying to measure position in a positive direction, right, if you're trying to measure the uncertainty in positive x direction, then your wavelength will shift in the negative y direction. You can actually see that from result, but I think that is not true because uncertainties are actually positive. If this equation, if that holds true, you can actually say there is no particle within that space. So if let us assume that you are measuring your particle in position x-axis, so right, so this would be your x-axis, this would be your, I'm just saying what will happen if you have taken negative sign and what would be your conclusion. So I had worked from that perspective also. As a physics student, I have already told everybody, you have to see from the all perspective, you have to think outside the box. So if you are observing a particle within this positive x-axis, right, and the equation would, let us just assume that we have to take the negative sign. So if we take the negative sign, our relation will be delta x into delta lambda. So there will be negative 2 pi over lambda square. So I am using the negative sign here. That would be greater or equal to lambda square upon 4 pi. So if you take this negative sign or inequality sign, which shifts, and you will end up getting delta x into delta lambda is less or equal negative lambda square upon 4 pi. So your uncertainty is actually negative here, and one can actually conclude that if let very much counterintuitive part here. Let us see here. So if your delta lambda you are measuring around certain positive x direction, there must be an negative uncertainty in wavelength, right? So in another form, you can actually think of it as like that. If you're measuring the uncertainty in wavelength in positive direction, there will be shift in position of particle in the negative direction. So I think this would not work. Or may it works, who knows about quantum mechanics. Anything can happen in quantum mechanics. So I'm just using the positive side. I know that the uncertainty are always positive. So what if uncertainty is actually negative? Right? Nobody knows. I guess. You can actually think, what do you really think the physicists do not have looked upon it on the negative side? They do. They do. They have to think outside the box, watching all the perspective and all the results and simultaneously. So basically, I got the position wavelength uncertainty relation. So you can actually ask me how you can change the position wavelength uncertainty in terms of position energy uncertainty. So there is a very beautiful relation. So this would be my equation number third. Let us assume, and I know whether it is Planck's radiation law or something. I'm using the name of Planck's, whether it is actually his law or not. Planck's radiation law. So from Planck's radiation law, I think whether it is his work is relation or not, but it can be written in the relation is nothing but the hf, and the frequency if you want to write in terms of wavelength you can write as hc over lambda. So this is the energy associated with the photons that you are measuring within that confined space, right? So this would be the energy of photon, right? So I had done the uncertainty calculation based on this fact, you can see. So I'm just using the same fact here, and I write delta E as my uncertainty, and I would find it based on that thing. I'll write as dE over d lambda into delta lambda. So one can actually think of it like this form. Why I have to follow you? I will make my own process. You can write as d lambda over dE and delta E. I have already told you. You have to think outside the box and you have to look from the all possible perspective. Even if you are not getting that point, there will be some hidden points within that fact. So I think it makes sense whether you take lambda here or energy in terms of right side, or you can just do whatever you want, but you have to follow the math correctly. So your uncertainty in energy is nothing but I can write energy as hc over lambda. So I can take the hc common from the derivative and I got d lambda inverse over d lambda. So if you are actually the higher level physics student, you will automatically understand this how I got lambda inverse, and I don't have to explain to you like that. So, and those who are not very much good at mathematics and derivatives and inverse function calculation, they will suffer here. I am not saying I am very good at math. I am also very bad at math. So my uncertainty would be, and already I have told you the uncertainty is actually positive, and I again get the negative sign, and this would be my hc over lambda into lambda. So I will get lambda square. Why am I writing like this? There is another counterintuitive part. There is an intuitive part. So basically, the uncertainty is energy can be written as hc over lambda. Look here. This is the total energy associated with photon. E over lambda delta lambda. So I want to make a substitution of delta lambda here, and I will end up getting the uncertainty relation, right? So what would I do? I will write my delta. I will make delta lambda alone, and I will get lambda over E delta E. So I think it actually make sense to you. If you have E over lambda here with going here, I don't have to explain this to the higher students who are watching this video. So who has very much good mathematics. So I can actually make the substitution here. So I can actually make a substitution. Here. So I can write delta lambda as lambda over E. And I'm using equation 4 in 3. So let's look up here. In terms of delta lambda, I am putting this substitution. Delta x delta lambda over E delta E is greater or equal greater or equal lambda square upon 4 pi. And from this here you can see that the one lambda will cancel out another lambda, and you will end up getting delta x into delta E is greater or equal to lambda upon, sorry, lambda E upon 4 pi. I think I haven't made any mistake up to here. Okay, and you can see the lambda E is product. This is the constant for a given particular photon. You can write his E lambda is hc. So you will end up getting delta x into delta lambda is greater or equal hc over 2 into 2 pi. Why I am making this? I want to write the Planck's constant in terms of reduced Planck's constant. So the delta x into delta E is nothing. It's greater or equal to h cot c over 2. H cut c over 2. So this is the very much beautiful equation. You can actually see from here that the position and uncertainty of a given particle in a vacuum is always constant, or it could be greater. But this have to be the minimum possible value is h cut c over 2 pi. Right? You can actually say this. You can actually predict this phenomena. If you had, I really don't know, I'm just letting this point right now, right here. Now, you can see that the product of energy and wavelength is nothing but the Planck's constant. So you can actually say that for every color photons, the position uncertainty and energy uncertainty, the product of these two is always constant for the every photons. Isn't that very much interesting? So you take red color photon and you have done the experiment, you will end up getting this result. And if you change the energy, you take the violet color, again your experimental result will be the same or will be the greater than this. So this is very much interesting thing about quantum mechanics. So you can actually say that the uncertainty of position and energy of a particular photon or every photon is independent of what? What I have to say? What? Independent of what? Independent of energy and wavelength. Because hc is always constant. So the actually uncertainty. So I had also verified it for the first time. What I have to say now? I'm just an undergraduate student, and I have derived this much equation, and I have to predict the fact that for every color I'm writing this, whether it hurts you or not, it doesn't matter because it makes sense for me. For you, it makes sense. Or let me clarify. For every color photons. For every color photons, you can see the visible spectrum, or you can say the gamma radiation. You can see the infrared, or the X-rays, or the ultraviolet radiation. For every color photons, the position, momentum, the position, energy, uncertainty is independent of wavelength and energy. So when the creator is creating these particles, he doesn't associate any energy or wavelength that could change their uncertainty. So the equation is how I am saying this. So I am saying this based on the fact that the product of energy and wavelength is always constant. So actually the Planck's constant and speed of light is constant for a vacuum. So this term always with a constant. So x is always constant for every photon in space. The uncertainty in position and the product of uncertainty in position and energy is always constant. So the every color photon, if you take every color photon in space and you perform an experiment, you will end up getting the minimum possible value this or greater than this. So actually you can say that the uncertainty relation is actually independent of energy and wavelength. So you can actually say like this. If you change the color of photon, you will automatically change its energy and its wavelength. But the wavelength and energy changes in such a manner there will be always constant quantity in vacuum. So this will be always, this term is always constant. This will be always constant. So for every color photon, the uncertainty is actually independent of energy and wavelength associated with that particle. So how the uncertainty is actually coming? How do you account for the uncertainty of this thing? So how now you are actually deriving in terms of energy and wavelength, but you get the uncertainty here is a constant. So what thing actually drives the uncertainty of photons? Is the God actually driving this? So I also don't know. You have to comment down below, right? I think it actually makes sense. Let me just, okay. I think it makes sense. So the video quality is very much low, but the knowledge I'm providing is very much right. I guess because I do not have any mentor or anyone whom I can actually show these ideas, because in my country there are no quantum physicists, right? Yes, I might be the one. I don't know. So okay. I don't want to bore you here. I'm just taking it to another level. So you will end up getting the uncertainty in position, and the energy is actually independent of energy and wavelength in vacuum. That is always constant. But but if we change the medium of a particle, what would be our uncertainty? I had already told you have to think outside of the box. You actually have to. So if we change the medium, we can write the refractive index as speed of light in vacuum with respect to speed of light in that particular medium. So I can write speed of light is refractive index mu times vacuum. So I can make a substitution here, and I will get delta x into delta E. So this is for our vacuum. I am writing suffix here. I think it is called suffix. Yes. I really don't know about it, but I think it's a suffix. Is greater or equal h squared, and in terms of C you can write mu v over 2. So you can actually see from here, I can, if you let me allow, so if you let me allow for an instant, I can write h squared v over 2 and mu. So doesn't this equation look familiar to you? Look. This is in the speed. This is the speed of light in vacuum, and this is the speed of light in medium. So h squared v over 2 pi would be a constant quantity for a given particular medium also, right? Yes. It would be also constant in a, because the speed of the change in speed actually is constant for a given particular medium. It would be 2 into 10 to the power 5 meter per second, or 2 into 10 to the power 2 into 10 to the power 8 meter per second. This would be constant. So if this is uncertainty and this is dimensionless, because the refractive index is actually dimensionless, so this is uncertainty and this is dimensionless, so these two equations must have the same dimension in order to get the dimensionless quantity. This is a very much fundamental thing about physics you have to know. If this is apple and this is also apple and this is nothingness, if you divide these two you will also get nothingness, whether it makes sense or not. I am saying what? This is meter per second, this is meter per second. So mu is actually unitless. Unitless. So in order to make the mu unitless, these two quantity must have to be the same unit. Right? So if this would be my uncertainty in position and energy in vacuum is greater or equal, I can write as uncertainty in position and energy in given medium M. M could be any medium. You can think about it, any medium, whether it is glass, it is air, whether it is oil, it is or plexi, or it is a paper, anything you can think of it. And this would be mu. From here you can see that there will be more uncertainty. So you can actually see the sound of free fire. So you can actually see there will be more uncertainty in which medium? Tell me. Tell me. There will be more uncertainty in vacuum as compared to given medium, right? There will be more uncertainty. If you take mu as 1, these two quantity would be same, right? Right. So if you take the ratio delta X into delta E in vacuum by delta X into delta E in a given medium, that is greater or equal mu. The ratio of two different uncertainty in different medium is always giving you the refractive index of medium. You can actually calculate the refractive index of medium by calculating the uncertainty with high degree of precision from here, right? I hope this also makes sense. So this also makes sense. With respect to medium, the uncertainty in vacuum is greater than that particular medium. So you can actually say the uncertainty is actually, I'm just doing here. I'm just making it sense. It has to make sense. You do not have to calculate the uncertainty over a different medium. If you had calculated the uncertainty in a given particular medium, right? In a vacuum, if you had calculated the uncertainty, and if you divide the quantity with respect with the medium, with a particular medium, if you want to calculate that uncertainty, you have to just divide and you will end up getting the uncertainty relation in that particular medium. So you can write here, what you can write here. So your delta X into delta E in vacuum divided by mu is greater or equal delta X into delta E in a given particular medium, right? So for an instant, let us just neglect this inequality sign and make this same. So delta X into delta E in a given medium M is equal to delta X into delta E in a vacuum divided by mu. So you can actually see from here the uncertainty in a given particular medium decreases 1 by mu times with respect to vacuum. So if we had an uncertainty, let us say 2, just what is it, just an example, and if you take the refractive index is what we have to say, let us say it's 2, the uncertainty would be 1. I'm just doing the nonsense example because you can see from here the uncertainty in another medium, you can actually see the uncertainty in another medium M is inversely proportional to the refractive index of medium. The uncertainty decreases with increase in uncertainty. So you can actually isolate because the minimum possible value of mu is 1. This is for vacuum. Right? Right. This is the minimum possible value in vacuum. But the refractive index increases with change in medium. So with increase in mu, your uncertainty will decreases. You can actually isolate a photon in another medium as compared to vacuum. So there will be more difficulty in isolating a photon in a vacuum as compared to the isolation of same photon in another medium. So in order to see the photon, you have to change the medium. You do not have to conduct an experiment in vacuum. It makes sense. So you can by using the relation, you can actually calculate for the different medium. Right? You can actually do the experiment for a different medium. So up to here, I think I do not make you bored. Or if you did not understand this, you can forget yourself. Don't blame yourself because every quantum physicist has already told that the quantum physics is actually non-intuitive. So you don't know what is really happening without performing an experiment. So I don't know really this works or not, but the mathematics says this thing and I had shared it with you. So up to there, bye bye.